Federal Drive is presented by GEHA, Government Employees Health Association, proudly providing health and dental benefits to federal employees and their families. Visit GEHA.com.
A new study from UC Riverside shows how linking smaller quantum chips can build larger, more reliable systems, even when those connections aren't flawless. The breakthrough could help scale quantum computing faster than expected without waiting for perfect hardware. Mohammed Shalby, the study's lead author, explains how this shift could reshape the future of computing. Mr. Shalby, thank you for joining me.
Thanks, Terry, for having us. Happy to be here.
Your team has just published some pretty interesting quantum research that says we don't need perfect hardware to scale quantum computers. Help us understand what that means in plain terms.
So I want to start by saying there was a saying in the field of quantum error correction that your device is as weak as your weakest link. So that was an informal saying, but that was like a belief we had. But in our work, which was like a step in a series of other theoretical foundations that built to this point. Anyways, we showed that under special conditions and with careful engineering, this is not necessarily true. The statement about weak links kind of like disrupting the entire system. So for limited use case, and in particular, the use case where we need to connect more than one device or more than one system together, the hardware there is kind of weaker in general, or usually have higher requirements than like the links that are within the chip or within one device itself. So anyways, we just had direct simulations, so strengthening the theoretical foundation that was out there, and we showed that you can get away with weak links. So we can use these weak links connecting the devices, and they will work as perfectly as we expect without the strict requirement of these links being like flawless.
So let me ask you a little bit more about that. I am not a quantum scientist and don't pretend to be. So what I understand is that connections between quantum chips can be noisy, and that's a problem. And what you showed was that even noisy connections can still support quantum calculations and error correction, and that's a real challenge to conventional thinking in quantum hardware design. If I've got that right, what does that mean for the future in terms of designing quantum systems?
So good question. Mainly, like theory has seen lots of rapid advancement in our work, and in also too many other great works by too many great talented scientists. And hardware is also picking up on that, which means that we are telling the hardware people or signaling to the hardware people that we could start to scale up quantum computers faster than we would have thought. We don't need to wait until each and every component is perfect to start scaling up. And we could already work with what's currently achieved. This means that hopefully the path towards a scalable quantum computer is a little closer than or hopefully a lot closer than what it used to be. Of course, with our work and like the other efforts, parallel efforts that are being currently done by like, the people in the field, too many talented people in the field.
So you feel like you're part of a wave of disruption in the quantum hardware space?
Well, I wouldn't say disruption, like a strong word. I mean, I understand the hype about like the risks and the benefits of quantum technology, but I see myself, yes, as a part of an amazing community of talented scientists all over the US working towards this goal of achieving quantum advantage.
I'm speaking with Mohammed Shalby. He's a doctoral researcher in quantum physics at the University of California, Riverside. So let's follow that thread for a minute, because your research has implications for quantum hardware. There's other things like superconducting materials and room temperature quantum bits I've read about. So are all of these things coming together to accelerate real-world applications of quantum computing?
Well, how would I put it? It's kind of like amazing to me when I get to see like, or when I go to a conference and you see how parallel efforts kind of like come together nicely. So you have people working on like hardware, all different kind of hardware, and from superconducting quantum bits to like trapped ion, cold atoms, like too many amazing people working on that front. But also on the algorithmic front or on the use case front, on like what would be a scalable quantum computer useful for? You also see a lot of people working on that even before we have the devices. And then like the error correction theory and experiment, which I would see myself a member of that community, we are like working hard to get this to speed, to get the hardware with the error correction ready for people who already have proposed applications that could be here once the hardware is there.
So, what sort of problems do you see this scalable quantum hardware working on? Is it climate science or cybersecurity, or what should we be expecting quantum to actually deliver in terms of process and product?
Well, there are some things that we are sure of, or that the application is clear, which is in communication, for example, secure communication in drug discovery, or like in material science and drug discovery. But also, what has been recently shown, experimentally shown, that quantum computers offer tremendous computational power. Like you just have unexplainable amount of computational power at your disposal. And too many people, and I personally think that once you have this, we will know what to do with it. I mean, the applications that yet to be discovered are, I think, are that the space is very open.
Your work suggests that we don't have to wait for perfect conditions to move forward. What message would you have for policymakers or tech leaders who might still be hesitant to invest in quantum infrastructure?
What I want to say is that quantum technology is promising a lot of advantages, and it's probably happening faster than we have thought before. The field is moving rapidly in the US and also globally. I mean, the competition is fierce on that front. And in order for the US to maintain the historic leadership in the field of quantum, the administration should keep investing in research done by, like, of course, professors and groups all over the like US institutions, universities, maybe also building more or like expanding the collaboration that we've seen between the government and the private sector recently. So yeah, I think the administration is doing great for like in terms of quantum, and we just hope it stays the same or even more.
I've been speaking with Mohammed Shalby. He's a doctoral researcher in quantum physics at the University of California, Riverside. Thanks for joining me and congratulations on your research.
Thank you so much, Terry. Happy to be here.
We'll post this interview at federalnewsnetwork.com/Federal Drive. Subscribe to the Federal Drive wherever you get your podcasts.